Hello my friends and welcome again to my video channel. Today we'll start a new project, DDS-4. It's a digital direct synthesizer for the Drake 4 line. It's not a genuine Drake product, it's a product by a ham who made it for the Drake 4 lines. So the design is very close to the Drake design, but again it's not a Drake product. This direct digital synthesizer replaces the internal PTO and crystal generator in the Drake 4 lines, and tuning is possible with only this one. Of course, the pre-selector has to be aligned properly by the 4 line, but let's have a look into the details. The owner claims that the output level of this synthesizer is too low, and he told me that maybe the output amplifier, it's an MMIC, a small MMIC type MAR8, is bad. I checked the output voltages and frequency on 28 MHz. By the way, this frequency, what's coming out here from the synthesizer is always, it's an injection frequency. For the 4 lines, it's always 5.645 MHz above the receive frequency. That's the first IF. And when we have a setting of 28 MHz, so the frequency is 33.645. That's okay. When I go down in the band, '24, and you see the amplitude drops. 21, 18, 14, 10, 7, 3 MHz band. This is not okay. And when the frequency increases, then the output increases also. That's not nice. I think there's something wrong. And another problem I have seen is this knob here. It's loose. I don't know what happened. It's a little bit not perfect to align. So I will try to repair it, to look what's going on there. The top cover is removed, and now we can have a look at it. This is the output board. Here we have the DDS. This is a low pass filter, the output transformer from the DDS for symmetrization output. Here we have the MMIC, this little spot. It's an ERA 1, not an MR8. As the owner said me, it's an ERA 1, it's a different version. And here we have a big transistor with a heatsink, and this is not original. This is a modification. I don't know exactly why there is a modification. In my opinion, it's not necessary, because the ERA 1 provides sufficient output power. This is the output cable to the output box. Output connector here. See the BNC connector. This one is a little bit suspicious. I don't know why someone has installed this transistor, and I will try to check now and redesign what this transistor is doing. Here we have the complete schematic of the output circuit. This is a DDS. It's the output, it's a symmetrical output. It is symmetrized by this transformer. As I see, the tapping here is not present, but the 2 resistors are installed. Each has 50 ohms, so I think it's sufficient to supply the positive voltage through these 2 resistors to the 2 outputs. So this tap is not absolutely necessary. I will check it, but this is not an explanation for the problems we have at low frequencies. The secondary side of the transformer is grounded. And here we have a low pass filter which goes to the ERA 1 input, output, and this should go directly to the output. This transistor here, I have found after some redesign and some examinations, it's a 2N5109 NPN. The base is connected to the output of the ERA 1. This coil is obviously shorted. We have a resistor of 220 ohm instead of 180. Okay. The collector is connected to the plus 8 volt and the emitter is grounded via a resistor. I couldn't see the value because it's on the bottom side of the board, and the output here is connected via capacitor to the output. These two caps are not existing, so we have here simply an emitter follower added to the output. It makes no sense. Emitter follower only amplifies the current but not the voltage. But we have a low voltage output, even unloaded, so I'm not sure what the intention was and why. This circuit would supply sufficient output power to the DDS-4 line. Why do we need here an additional transistor? Maybe someone tried to compensate the problem, which is maybe here in the output of the DDS, and tried to compensate this problem with a solution, but this is another problem. My first check now is I will check the output of this chain here of the low pass filter, whether we have here a signal with constant amplitude over the whole frequency range. The scope is connected with channel 1, it's a yellow channel, to the input of the MMIC, directly connected here, and the output, the blue channel, is connected here, out 1 to the BNC connector, which is a blue channel where we have the variation of the output of the amplitude versus frequency. So we compare this input to this output and see what happens. We are in the 28 MHz band. We have the rather high output with 33.64 something. Again, 5.645 MHz above the band setting or frequency setting. When we go down in the band, 24 MHz, you see this voltage stops, but the yellow, we go back, the amplitude, the yellow trace is constant. Now we are at 18 MHz, 14 MHz, and you see 7 MHz, 3.8 MHz. So you see the yellow amplitude, the yellow channel, which is channel 1, which is connected to the input of the MMIC, is always constant. The problem is the output, which goes up with higher frequencies. So it's a little bit suspicious. I will measure now the output of the MMIC. Now I'm measuring the input voltage of the MMIC. This is the yellow line. It's a rather small signal, as we have seen. And now I'm going to the output side of the MMIC. The signal is much smaller on the output than on the input. This indicates to me that we have a problem with the MMIC itself. But what I really don't understand, the output signal, the blue line, is much higher than the yellow one. When I connect the yellow one to the output, also where the blue line is, both should be identical, but they are not. And I see I have maybe a problem with ground connections. There's a phase shift. Or is it a resonance effect? Okay, I'm using a coax cable. I will use a 50 ohm feed through attenuation termination, not attenuation, a 50 ohm termination, to see whether it's a resonance effect. Now we have a 50 ohm termination. You see the signal dropped considerably in the output. But again, the yellow one should be identical with the blue one. Same, not the same sensitivity. Sorry. When I go to, okay, now it's correct. Both have 500 millivolts. I need a little bit more. Now they are identical. When I have a 50 ohm termination, so maybe there's a resonance on the cable, which made me a little bit confused. But still the problem occurs. This is the input of the MMIC, and this is the output. So the MMIC has a problem. When I go down in the band, (7 MHz), for example, Okay, we have more input. And the output is the same now. There is something wrong on this board. Maybe we have a ground problem, a grounding problem. There are two separate boards, whether the ground is not connected properly or we have other problems. I will remove the transistor, the modification, and swap the MMIC, and then we can see what happens. Now it's time to swap the MMIC in the output of the synthesizer, but first we should have a look at the levels we are talking about. Many years ago I made a measurement in my Drake C line on the injection levels of the receiver, transmitter, and in the separate position the injection cable between the receiver and the transmitter is a connection of the injection signal when we are in separate position. So I could measure voltages approximately in the range of 1.4 volt peak, 1.2 volt peak at various frequencies. The highest level I've measured is 1.4 volt peak. That's 0.5 volt RMS, corresponding to approximately 5 milliwatt. That's 7 dBm at 50 ohms. And I never saw a higher value than this 1.4 volt peak. In position receive, the levels are a little bit lower, also in the position transmitter. So in general, I can say the maximum level we need is 7 dBm, assuming 50 ohms, which is of course not correct, because this signals here do not have an impedance of 50 ohms, but just to have an imagination at which levels we are, these are the levels we need. And if we need only the voltage, then we could use an MMIC which produces 7 dBm. This would be 500 millivolts RMS at 50 ohm. If the load is less than 50 ohms, it means more load impedance. Then we would have, of course, a higher voltage there, which is sufficient. Now let's have a look into the data sheet of the MMICs. The MAR8A, new is relative. The data sheet is, I think it's from the year 2000 or so. I don't see a date on it, but as I know it's a rather old one. Has a gain of 31 dB at 100 megahertz. The maximum output power is 12 dBm. That's more than the 7 dBm we have calculated, and 12 dBm is at 50 ohm load. So it could be a solution to use the MAR8. A is important because the old MAR8 without A is a little bit unstable regarding self-oscillation. Here it is stated with improved stability. Okay, that's one option. By the way, the biasing is done with a resistor, and the choke, radio frequency choke, is optional. I see sometimes solutions where the biasing resistor is blocked with a capacity to ground, and only the choke here is the biasing impedance. That's not a good solution here, because we have frequencies between 7 megahertz when we use it for the R4C. Operating frequency 1.5 megahertz, we add 5.6 megahertz IF, so we come to 7 megahertz, and the highest operating frequency is approximately 35 megahertz. Reception frequency 30 megahertz plus 5 for the IF, 35, so the relation is between 7 megahertz and 35 megahertz. So such a choke alone is not a good idea. It's better to have a biasing resistor, and for 12 volt, for example, we need 220 ohms. We have 12 volt supply internally, so the 220 ohm could be a solution. The other one is the ERA, what is it? ERA 1, what is stated. So let's have a look at the data sheet for this MMIC. This is the data for the ERA 1. ERA 1 is not specified at 100 megahertz, 500 megahertz and 1 gigahertz. Only beginning with 2 gigahertz. The gain is specified with 11.6 dB, we can assume that at lower frequency it also has not more than 11 or 12 dB. It is specified on the other hand up to 8 gigahertz. Okay, we don't need this, not necessary. The output power is 13 dBm at 2 gigahertz. The MAR8A has 12.5. Here we have 13 dBm. Noise figure is a little bit worse. It's 7. Well, the noise figure, I think it's not decisive, and the IP3 also not. So I think that the MAR8A is a better solution for our application here, because it is specified at lower frequencies and has more gain. It's specified between DC and 1000 megahertz and not more. We do not need more, but therefore we have a little bit more gain, and the output power is the same. So we will replace the IC which is on the board by an MAR8A. The old era 1 is out, this one. The pins are cleaned with some solder wick. This output capacitor, it is not installed here because we had a modification which I have to redo, but at the moment I leave it without output coupling capacitor. I only replace in the first step this MMIC. This is a new one, MAR8A. We have to look for the orientation. That's the input. We have here a small index on the wire. You can see it here. There's a dot on the case. We need, at least I need a magnifying glass, and it's also cut a little bit diagonal. So we have an index here and here. These two leads are the ground, so it is not relevant whether it is installed this way or this way. Input, output, and these are the ground. As we see, 2 and 4. We have to cut the wires a little bit because they are a little bit too long for the board layout. I will do this now. The new MMIC is in place, but before we can continue, we have to unmount and redo this modification here. The wire is obviously cut, as I see. So the connection of the coupling capacitor to the output pin is interrupted. It has been done on the bottom side due to the modification. Well, I will remove this resistor and this SMD capacitor. The resistor is removed. By the way, it was the resistor to ground for the emitter follower. An emitter follower needs a resistor from the emitter to ground for correct biasing. And the wire is resoldered again with a bridge. And on the top side now we have here coupling capacitor and the output of the MMIC. So we should have here a signal now, fully amplified, and we will measure it now. The board is in place again. All wires are connected. A probe is connected. It is set to 1 by 1. And now we can have a look at the output of the signal generator. It is of course unloaded because we have a load of 1 megohm, just to check whether it is working now, and we can check the parameters later. This is the output signal for 1.1 megahertz. Reception, the frequency is 5.6 megahertz above, so 6.7 megahertz. When I go up in the band, sorry, it was the wrong direction. 3.7 megahertz, that means 80 meter band, 40 meter, 30 meter, 20 meter, 18 megahertz, 21 megahertz, and 24 megahertz, and 28. So we see the output amplitude is constant. We have there's some noise on the cable. Okay. we have 1 volt per division, so totally, you can read it here, 1 volt per division, so we have totally an amplitude of 1, 2, 3, 4, it's approximately 5 volt. When we shift it a little bit, yes, it's 5 volt. Peak to peak. And now I will connect an R4C and check how it works. Now a short check of the output amplitude of the DDS-4 when connected to the R4C, that means with load. We also have an output voltage of nearly 5 volt peak peak. This is 2.4 volt, 2.2 peak, so we have 4.6. When it is obviously perfectly aligned or tuned, not aligned, tuned. When I detune the signal with the preselector, you see the signal goes down and the output changes the shape, but it's not relevant, it's always constant. So we can peak the signal of the calibrator. We are on the 80 meter band, 3.8 megahertz. When I remove the load from the DDS, unplug the cable, then we have a square wave output nearly, so it's okay. And now I will check it on the other end of the band, on the 10 meter band. 28,500. It is peaked, where the output voltage is a little bit less. As we see, we only have 2.5 volt peak. And when I unplug the R4C, the signal increases, but that's not relevant. We still have for the calibrator 9 plus 20 dBm. When I switch on to the normal position and unplug the DDS, we have a little bit less signal. That means the DDS-4 produces a little bit more injection power than the R4C itself. Okay, we can leave it as it is. I can't change the concept. The result of this short test is we do not need any output amplifier to decrease the output impedance. The signal is strong enough to drive an R4C and even, I am sure, to drive a T4XC. One thing could be done, the cable is a little bit long in my opinion. The coax cable between the R4C and the synthesizer, it's a rather long cable, not necessary. The capacity is a little bit high. It could be reduced, the capacity, by cutting the cable, but this is another topic. I don't do it. It's not my task here. Well, that's it with the test. And now the test of the function. First, I'm operating the R4C standalone. The DDS-4 is switched off. I tuned in the calibrator signal at 28,500. Peaked it for maximum with the preselector. And then I do the same now with the DDS-4 and I switch off the internal crystal, set it to extern. Extern means that it waits for the FS4 signal, but there is no FS4. The Drake synthesizer is not connected, so I have to go up with the band. (28). And we see the signal is a little bit stronger. With this, it's 28,500. Then with the internal signal, we go down to 14 megahertz. It's 14250. Okay, 9 plus 60. It's a very strong signal. Go down to 7 megahertz. Seven dot 100. This is the even harmonic. When I go 125, you see the signal is stronger. The odd ones are always stronger than the even ones. Go down to 3.5. Band is function. Ah, sorry. This one. 3750. Is this right? Yes. It's also okay. We see we have a strong calibrator signal over the whole band, and the DDS-4 now is again working. Now we are at the end of this project. It was a rather simple project. We only had a bad MMIC. The MAR8A was bad, or another, the ERA1, but I replaced it by the MAR8A version. This also is what the owner wanted. And there was a modification inside. I really don't understand why this modification reduced the output impedance, but I don't think it is necessary. We see it works. Even with a T4XC in parallel, we will not have problems, because the injection signal is not heavily loaded. The injection connection is the tapping of an input filter, which is tuned. And when the filter is tuned, the impedance goes high and not low. So I think it will also work with a T4XC in parallel. Okay, it can go back to the owner. Stay healthy, stay tuned. See you on this channel.